All right, let's jump into this. So I have your tests to give back, but I will give those back at the end. So I don't want you looking through your tests while I'm up here talking about stuff. So in the meantime, we're just going to jump into it. Not going to do much today. We're going to cover the next topic in your textbook, which I don't remember what it is, 3.5 maybe. Linear approximation and marginal functions, which is an economics term. Linear approximation and marginal functions. We're only going to do linear approximation today, which shouldn't be too bad. And it was covered by one of the bonus problems in the test. So by the end of today, if you didn't know how to do one of the bonus problems, you'll do the other. You'll know how to do it. The other bonus was on like L'Hopital's rule and stuff like that. Let's talk about linear approximation. They're two very different things. They both involve the derivative, but they're, as far as topics go, two separate things. I'm not even sure why the textbook dealt with them both in the same section, but it does. Let's talk about linear approximation first. So that's the one we're going to do here. And the idea is using the tangent line, or a tangent line, using a tangent line, which is a linear function, to approximate the output of a function. So this is called linear approximation because you use a line to make the approximation. So the idea here is, where does this idea comes from? Well, you can imagine a little picture here. I'll tell you where the basic idea comes from. You have some function doing as it doing whatever it wants. Okay, so that's your function. We can call this f of x. And let's say there is some point on this function for which I know all the values. So this is some particular x value, let's call it a. And of course I know the output of that x value, let's call it f of a. Okay. And here's kind of the setup. There's some other point, x, right? I'm calling this one x because it can be a variable. It's just whatever other point you're interested in at the time. So a is a fixed point. You know everything about the function at that point. X is some other point over here. Now, of course, it has the corresponding value, f of x. Right. Now, the goal is to approximate f of x, given that you know what f of a is, and you actually know also what the derivative evaluated at a is. Because what we're going to do is, in order to approximate what the output at x is we're going to use a tangent line. So I know what f of a is, I also know what f prime of a is. So using that, I can actually construct a tangent line passing through that point, right? So this is a tangent line. So now here's kind of the basic setup. If I were to measure the difference in the two outputs of the function, right? So these are two y values, like y1 and y2. If I were to measure the difference in those y values, this is what we call delta y, change in y. And if I know about the change in y, I can tell you exactly what f of x is because I know what the original y value is. If I know the change, I'll be able to subtract that from that and figure out what this guy is. But let's say I don't know that. So what we do instead is we keep this guy going up. So we find what would the output have been for that x value on the tangent line. And that's just going to be the equation of a straight line. We're going to know what that actually is, right? Now, the difference between the y value for the tangent line and the original y value, that's also another difference. We call that one dy, right? As in the numerator of the Leibniz notation, right? So delta y is the actual change in the y value. Dy is the approximation of this change from the tangent line. Similarly, delta x is the distance between here. It's actually the same as dx, but whatever. So now here's the idea. These two guys, the closer I get to where the tangent line is based, right? Remember the point of a tangent line is that if you zoom in far enough, it starts to look more and more like a function, which means that these two values actually start to get closer together the closer I get to this point at A. And so the idea here is when x is close to A, and that's the operative word here, if my x and A values are very close, then my delta y and dy will be close. Which means the output of my function will be roughly equal to whatever the output of the y, which this is the y for the tangent line. Right? The y value for the tangent line and the y value of my function, they'll start to get very close the closer I get that x to A. Now how do you find the y value for the tangent line? Well, we know the point. The point is A comma f of A. So I can take that to be x1, y1. And I know the slope. The slope is just the derivative evaluated at A. And under assumption, I know what that is as well. So that's my m. And so I can use y minus y1 equals m x minus x1. And so that would mean y minus f of A is equal to f prime of A times x minus A. And so my y for the tangent line will be f of A plus f prime of A times x minus A. Right? So this leads to the following approximate equation. My f of x is going to be approximately the same as this particular output that we just derived. F of A plus f prime of A times x minus A. This guy here is called the linear approximation formula. So what I want you to notice is that this tells me approximately what my f of x is equal to. My f of x is approximated by this quantity. Now my f of a is a known value, my f prime of a is a known value, and this is just a difference between the x and the a. Now, the closer x is to a, or a is to x, I really want to put it, closer x is to a, the better the approximation. If you go far enough, then the approximation is going to be absolutely useless. But there comes a point where getting close starts to make the approximation kind of, well, very useful. The better the approximation. So for linear approximation, this is the main formula that you want to remember. My y value is going to be approximately equal to that expression where my f of a is some particular y value that I know all the information for at that y value. So that's basically the gist of it. Let's actually apply this formula in what may seem like a very silly example. But it is the type of question that I would ask, as well as in principle, it will show you something very important about what's going on here. Let's do an example. So the problem I would ask you here would look very similar to how I asked in the bonus. Something like use linear approximation to estimate the value of this expression. 3.99, square root of 3.99. Approximately what is that? Using a linear approximation. Which means ultimately, I'm going to want to be able to somehow use this formula to help me come up with an estimate of what the value of that expression is. Okay, so here's how you would go about doing it. So the first thing you're going to want to do is, of course, your formula here is talking about some function f of x. So it would be good to actually set up a function. Right? So I'm going to want to set up an appropriate function that is going to somehow, its outputs are going to help me get to the square root of 3.99. What do you think a good function would be? Yeah? Square root of x seems like a perfectly good choice. So I'm going to say set f of x to be the square root of x. Now, of course, I want what its output is when x is 3.99, right? Which is not something that I really know about off the top of my head anyway. Okay, so that's going to set up a function. The next thing you're going to want to do is to choose your a and x's, okay? So your x, this is going to be the value that you care about. Remember that value that you want to approximate the output at. So your x is actually going to be that 3.99. Now your a is going to be, the closer x is to a, the better the approximation. So now your goal is, can I think of a number that's super close to 3.99 for which I know the value? Yeah? 4. That's going to be the obvious choice. Now, again, it's worth mentioning, there are tons of numbers for which we know what the square root is. We know the square root of 1, we know the square root of 16, we know the square root of 36, we know the square root of a bunch of things. But 4 is the one that's closest. The closer we can get to what we want to approximate, the better. So I'm going to choose a value that I know the square root of, that at the same time it's super close to 3.99. So x is the actual input we care about. Notice that it's going to be messy. It's the thing that we don't really have all the info for. A is a nicer value. Nicer in the sense that it's more easy to compute. Close to x, for which we have all the info. By info, I mean specifically, I know what the output at that point is, and I would know what the output of the derivative at that point is. So 4 seems like a very nice, solid number to make that guesstimate. So the third thing we're going to want to do now, so I set up a function, I know who my x and my a are. The third thing I'm going to want to do is actually find the pieces that are going to go into this formula. So I need to actually find my f of a and my f prime of a. Now, of course, your f of x is the square root of x. This means that your f of a, in this case, your a is 4. So my f of a is actually f of 4, which is the square root of 4, which is 2. I know that value. We also know that f prime of x is 1 over 2 radical x. We know that for a long time in this particular instance. Which means my f prime of a is going to be equal to f prime evaluated at 4, which is 1 over 2 times the radical of 4, which is a quarter. So that's the pieces that I would need for the formula. So 4, now you plug into the linear approximation formula. So for this, you're going to have that formula memorized. So of course, we copy things down that we want to memorize every time so that eventually by the time the test comes around, we have it memorized. So that's the formula I want to use, recopy it. Now, and we can note, just to remember what we're doing here, the square root of 3.99 is actually just f evaluated at 3.99. Those two are the same, right? Which means using this formula, I would be able to say that the square root of 3.99, well, that is just f of 3.99, but this is approximately equal to f of 4 plus f prime of 4 times x, which my x in this case is 3.99 minus 4. And now I'm just plugging in the values. F of 4, 2. F prime of 4, quarter. 3.99 minus 4, minus 0.01. Notice that I can write that as minus 1 over 100. This is 2 minus 1 over 400. 2 is 800 over 400, so this is 799 over 400. And that would be my approximation. That would be my guess as to what the square root of 3.99 is. Now, just for fun, what is that? So, if I took 799 divided by 400, so this is actually 1.9975. So that's my guess. So this is the estimate for what this is. Now, in a test, this is your answer, right? Because you won't be able to use a calculator. But just for comparison's sake, compared to, let's look at the actual answer. So let's, we did this by hand, nothing up my sleeves, I just got that estimation. Let's see how close we actually are. If I actually type into my calculator the square root of 3.99, the actual answer is, ready? 1.9. So far so good. 7. 4. Yeah, okay, so we're but in all fairness, the next number is actually 9, 8, 4, 3, da da da. If I were to round, I just got to the answer to within 4 decimal places with rounding, without a calculator. So, when people are like, you know, what's the point of calculus? So just show them this, like, oh my God, how'd you do that on a calculator? And just like dazzle them, like, yeah. This is, so I spend my life learning calculus. No, there's actually a very important thing. So this is really cool. Of course, I could do this radical of 3.99 without a calculator, and I can get it right up to 4 decimal places if you allow me to round. But why is something like that actually important? I want you to appreciate what we actually did here. There was a function, square root of x. And I knew about one point on that function. Specifically, I knew when I was at 4, the output was 2. right? And then there was some other value that was close to that I cared about, right? So there was a point over here, 3.99, and what that was, I had no clue, right? And without actually using the function itself, without me going through the square root function, in fact, I used the equation of a straight line to actually guess what that answer would be. And my guess, using a straight line, so if I took a tangent line at this point, and I plug this input into the tangent line, the output of that tangent line was 799 over 400, right? And I used that value to guess what this value was, and didn't do half bad, right? Now, depending on the context, 4 decimal places might be good enough, it might not be good enough, but it kind of shows you what the possibilities are. Now, how is this actually used? And is this actually worth anything, or is it actually a party trick? Right, just to like freak people out. Well, one thing we know this works and we know it used, there are many examples, but I guess one of the more drastic examples would be like investment guys make billions of dollars using this kind of idea, right? So you have a function, let's say it's measuring the price of a stock, right? Very complicated function. You don't know what it's going to do in the next moment, right? So you're measuring it over time, and you're talking about the price of something. And right now, you are in the present, right? Now, the question is, what is that guy going to do next, right? That is the goal, right? Because if you can predict what it's going to do next, of course, you can kind of set things up to benefit from it, right? So if you expect the thing is going to go up, what you're going to do is you're going to buy more of that thing and sell it later so that you can make money. If you think the thing is going to go down, you might short the stock, you might sell what you have now so that you won't lose as much, right? But knowing what's going to happen next is a very complicated question. How do you actually go about doing that? Well, one way to do this, it's not the only way, and sometimes you combine this way with other methods or other financial models, well, is to just like somehow find a way to create a tangent line here. And what you would guess it's going to do at some time in the future, you would just guess, oh, it's going to be here. Right? You just make that guess, right? And you're like, does that actually work out? Well, yeah, because they actually do this, right? And so, of course, now, very complicated function, and of course, you have to be very close for the approximation to be good enough. But they can get very close. They can do this to predict where the price is going to be 1 second from now, half a second from now. Not a very large time interval, and it's not enough time for any human to actually do anything with that information. But if you have a supercomputer doing trading for you, a second, come on, we can do millions of trades in a second. We can do I can buy and sell millions of stocks in that 1 second, right? So while a person might not be able to do anything, you can teach a computer to make a prediction, and then based on what's going to happen, buy or sell a bunch of stocks in this 1 minute, in this 1 second window. And then you're not going to be perfect because the future is not predictable, but you're going to be good enough to make a profit. Sure, you might lose in the 4th decimal place, but you would have gained in the first 3 decimal places. So you like, we'd make $5 billion, but we'd kind of be wrong by 500,000. We still made $5 billion, right? So once you can get a tolerance for how right you can be, the wrongness isn't going to matter as much. And so, yeah, that's how they actually kind of do these things, right? So nothing is more complicated for a function than actually predict what it's about to do. Like, you don't know a formula for this, you don't know what's going to happen. You have no way to predict what the next output value is going to be. But using this method and methods like it, you can make predictions, which is what is important here. And linear approximation from calculus, of course, at this point, it's multivariable calculus, like a Calc 3 version of this goes on in the computer. And you can actually make predictions, and they actually can make a profit from one of these things. So that's just one way in which you can do it. So the idea is your function is very complicated. Perhaps the function doesn't even exist yet. But what you can do is you can use a very simple function, namely the equation of a line, to make a prediction for what your function is going to do. And in a small window, you're not going to be that wrong, right? And that's just something that's a peculiarity of our universe. From one small moment to the next, not much drastic change is going to happen. So I know, like in mathematics, we study functions that do some strange behavior, like shoots up to infinity or something like that. But in real life, that doesn't really happen unless there's some sort of catastrophe, right? So if a function is here, it's not going to do something drastic within the next second if it's actually measuring something in the real world. It'll incrementally change. And so what you just want to do is guess what that increment is going to be. So within a small window, you can guess an increment. You're definitely going to be wrong, but the idea is, how can you be the least wrong possible? And how can you make predictions based on that and benefit from it? Yeah.
Like, how far ahead would you say that it's possible to like predict like a change?
Oh, it depends on context.
Okay.
And the idea is getting as close as possible.
Right.
Right? So a lot of the research, a lot of the new technologies that were being developed is just kind of shortening the window. So the shorter you can get that window, the better your prediction is going to be. So to go with this example, why would an investment bank hire a financial analyst that knows a lot of math and coding, right? It's because they want them to invent a method to get a shorter window. Like, yeah, we have a window now, but Goldman Sachs down the road has an even shorter window to work with. They're making more money than us. How can we shorten our window? Hire this kid out of college that knows about the math, that he can program a computer to get the window shorter, right? What method can you throw on top of this to make your prediction tighter, right? So now, the tolerance is going to depend. Like, if we're talking about trading, for example, then a second is forever. It's way too long, right? So how can I get it to a half a second, a quarter of a second, a thousandth of a second, right? What information can I find out in that window? And how do we keep pushing that window shorter, right? So it would depend on context. But yeah, the closer you can get these numbers to be, the better your approximation is. And yeah, these things are actually used in everyday life. Now, of course, we did a Mickey Mouse version of the problem, because this is applied calculus, but the principle behind this is actually applied in some very sophisticated scenarios. And we actually need some higher level calculus to actually pull it off. It'll be a mixture of calculus, probability, statistics, linear algebra, and some computer science to kind of pull off this kind of thing on a larger scale. But it is done, and this idea is used. Let's bring it back to Math 1203. Do the same thing for this guy. So I'll give you guys about 5 minutes to do this one. Use linear approximation to estimate the cube root of 8.01. So actually run through the method. Let me see what answer you get. Let me know that you actually follow the system. And then we will. So try that. more seconds to wrap up here. Okay, how do we go about approximating this? What's the first step? Yeah,
Set up your function as f of x equals cubic root of x.
cube root of x, seems like a good choice here, yeah? Then,
Set x as 8.01, y as 8.
a is 8. So we want a close number to the original value. That's nice in the sense I would know what the cube root is, and I would know what the derivative of this is evaluated at that point. Then,
Bring in a in the function. So f of a equals f of 8, which is the cubic root of 8, which is 2.
mhm.
And then find the derivative of the function. 1 over 3 cubic root of x squared.
Right, so this guy you just think of as x to the 1/3, do the power rule. So this means that your f prime is going to be 1/3 x to the minus 2/3, you can bring that under. And x to the 2/3 is cube root of x squared. You can put the square on the inside or the outside, but it's gonna be easier to do it on the outside. So here if I did f prime of a, that's just f prime of 8. It's just 1 over 3 times the cube root of 8 squared. So it's easier for me to take the cube root before the square, and so that's what I'm gonna do. Cube root of 8 is 2, you square that, you get 4, multiply by 3, you get 12. So it's 1 over 12. Okay, so now what?
Plug into linear approximation formula.
Right. So the cube root of 8.01 is going to be approximately equal to f of 8 plus f prime of 8 times 8.01 minus 8. It's going to be 2 plus 1 over 12 times 0.01. 2 plus 1 over 1200, because that I can just think of as 1 over 100. That's 2400 over 1200, so that's 2401 over 1200. And that would be our guess, that would be our answer. Did everyone get that? So if I actually try that, 2401 over 1200. So this is 2.0000833, and I think the 3's just repeat. Actual answer. Of course, it's still going to be a decimal approximation. I'm just, as far as my calculator can give me. So if I were to actually find 8.01 raised to the 1/3 power. Okay, so the actual answer, 2.0008. Get up to 5 decimal places already. 2. Well, the next one is a 9, so, I mean, if you allow me with rounding, I'm good up to 6 decimal places, so, not bad, 986. that's our guess, that's what the actual answer is. We're pretty close. And I used the equation of a straight line to guess what a cube root was doing. So the cube root function, you know, looks like that. So at some point, I knew what it was doing at 8, and I wanted to guess. At some point in the future, like 0.01 time in the future, what is that value going to be? That's my guess. That's what the actual value is. And it's pretty close. Pretty close. So we'll stop there. We'll do marginal functions next time. It's another thing that's usually applied in an economics context. This context can apply to anything. So I gave the example with like stocks and prices. But you could have done this with anything, like a population or the growth of a virus or whatever. You can make predictions using tangibles. It's like it's a thing. I will. Huh?
We're just talking about coronavirus.
The coronavirus predictions.
Wait, are we getting our test back?
Oh yes. Let me give you your test back. So